Hello and welcome. This is Bhaskar Napte from Pharma Growth Hub. So we use carrier gas into the gas chromatography to enable interaction of solute with the stationary phase and to carry out the solute out of the column to get the detection happen. Now there are several carrier gases used during the analysis like hydrogen, helium and nitrogen. Now why the hydrogen is the best carrier gas? That is the point of discussion today. So I'm going to explain you why hydrogen wins over helium and the nitrogen. And these are the point number four. These are the 3 points especially through which we are going to understand it. The first point is, the dispersion time of analyte in carrier gas. How this dispersion time impacts the chromatographic performance. The second point, we will talk about the speed of analysis. It is very important point. So why hydrogen enables the speed or why hydrogen brings the high separation, high resolution and reduces the analysis time. The third point is the viscosity of the gas. So what is the implication of the viscosity and how the hydrogen wins over the helium and nitrogen? And the fourth point is nothing but the conclusion. So we are going to talk about the overall summary and going to decide why hydrogen is the best carrier gas for the gas chromatography, especially using flame ionization detector. So the first point is the dispersion time of analyte in carrier gas. So dispersion time of analyte in carrier gas is proportional to molecular size of carrier gas. Now before we compare this molecular size and the rate of dispersion, first understand what is meant by dispersion. See, as a part of chromatography, your solute is maybe undergoing absorption, desorption, or partitioning between stationary phase and the mobile phase. Now, during this transfer of the solute between carrier gas and the stationary phase, the solute will also take some amount of time to get properly mixed with the phase. For example, if the solute comes in the carrier gas, now the solute will take some amount of time to get properly mixed with the carrier gas. It will spread inside the carrier gas, and this spreading time, this properly mixing time, getting gel with the carrier gas, is called as the dispersion time. Is called as the dispersion time of analyte in the given carrier gas. So the dispersion of analyte or solute is depends on to the molecular size of the carrier gas. And what the point says that the dispersion time of analyte will be more in case if the molecular size is more, or the dispersion time will be less in case if the molecular size of the carrier gas is less. So we have three carrier gases, the first one is nitrogen, helium and hydrogen. So which carrier gas has the highest molecular size? And it is the nitrogen, right? Then comes the helium, and lastly it is the hydrogen. So nitrogen is having higher molecular size and the hydrogen is having the least molecular size between these three carrier gases. So according to this definition, that the dispersion time of analyte is proportional to the molecular size of the carrier gas, it is obvious that the analyte will take more time for dispersion with the nitrogen as a carrier gas. Then comes the helium and finally the hydrogen. Or in another word, the analyte will take little amount of time, the least amount of time for the dispersion in case if the carrier gas is the hydrogen. Similarly, the analyte will take more amount of time for the dispersion in case if the nitrogen is the carrier gas. But what happens if the dispersion time is higher? Now, unless and until we connect this dispersion time with the chromatographic performance, this point will be a meaningless. And for that reason, let us now connect the dispersion time with the chromatographic performance. So what happens if the dispersion time is higher, like in the case of nitrogen? Solute is going to spend more time in carrier gas and less time in stationary phase. Now, why I am making this statement? The solute is going to spend more time in carrier gas. Let's understand this first. As the dispersion time is more for the analyte in case of higher molecular size carrier gas like nitrogen, it will take more time to disperse in the carrier gas. And as a part of this, the solute will spend more time in the carrier gas, and as it is spending more time in the carrier gas, it is going to have a lesser time to spend with the stationary phase because the dispersion time is more. See, the solute is always under partitioning or desorption absorption process. So the solute is going to enter into the stationary phase, coming out of the stationary phase, again enter into the gaseous phase, and again going back to the stationary phase. So this is the cycle happening continuously inside the column that we never see. But what is the important point for here is that, in case if the solute molecules comes inside the carrier gas, it is expected that it is now going to get back inside the stationary phase. But here, the carrier gas, if it is having the more molecular size, it takes more time for dispersion of your solute. And that makes the analyte, whether the analyte like or doesn't like, but it will spend more time with the carrier gas because the dispersion is still under the process. And unless and until it brings to, it gets to an equilibrium, the analyte will not go back into the stationary phase, and hence the solute spend more time in carrier gas and less time in stationary phase in case if the dispersion time is higher, or in case if the carrier gas is having the higher molecular size. Now the next point is very important, and we want to connect this spending more time of solute in carrier gas. So what this result in? Now this result in unavailability of solute for partitioning with the column. As the solute is itself busy getting dispersed inside the carrier gas, it will have less time to get partitioned with the column. This is very important point. The second point is what? The low plate count. Now why there will be low plate count? What is the plate count refer? The plate count refers the interaction of solute with the stationary phase. So more are the interaction of solute with stationary phase, the higher will be the plate count. But in this case, if the molecular mass is more, if there is a good amount of dispersion time, then there will be a lack of interaction of solute with stationary phase because the solute is busy interacting with the carrier gas, busy for the dispersion, and hence the solute will have lesser interaction with the stationary phase, and that can result into a low number of plate count. The third point is peak broadening. Now why the peak gets broadened? Because the solute is getting dispersed inside the carrier gas, and this dispersion itself is going to spread the band of the analyte. So more amount of time the solute spent with the carrier gas, the higher will be the spread of the band. And because of that, the peak will get broadened, right? And that can also impact negatively onto the resolution. And why the poor retention? The last point is poor retention as the solute flows more with the carrier gas and less with the column. So where is the interaction of solute with the stationary phase? Because it is busy being getting dispersed inside the carrier gas. and the carrier gas is flowing right with your velocity or the flow, and that is going to take the solute along with it itself. So the solute will get lesser time for the interaction with the stationary phase, as the carrier gas is not stable. As the gas is not still, it is flowing inside the column, and hence as the solute is present inside the carrier gas, it will get carried away with the carrier gas, and hence it will have the poor retention. So this is the impact of the higher dispersion time of analyte in the carrier gas. Let us analyze further. So the nitrogen is going to bring high peak broadening. If you understand the last discussion, it will end up with the poor retention with the similar kind of velocities as like helium and the hydrogen. It will bring the less plate counts and the poor resolution. What is going to happen with the helium? Helium will bring the low peak broadening, will be much better than the hydrogen. The performance of helium is not bad. As compared to nitrogen, it is very good. So it will bring a low peak broadening. So the peak width will be reduced. It will have the good retention. The helium, it's not having that much amount of molecular size. Nitrogen is with 14 and helium is with just 4. So there is a good amount of reduction into the molecular size. So the retention time will be good in terms of helium. It will bring the good plate count and good resolution too. And lastly, the hydrogen. It will not have much peak broadening, no peak broadening, excellent retention, excellent plate count, and excellent resolution. So I hope you understand how this comparison has been made. It is only based on to this particular box, what it result as the end point of higher dispersion. And the last one, what is the conclusion? Hydrogen wins over helium as well as nitrogen. So this is the first point. We talked about how the hydrogen is better carrier gas just because of this analyte requires minimum time for dispersion inside hydrogen. The second point is the speed of analysis. Everyone, are looking for the faster analytical method. The throughput should be high, and that is going to determine by the carrier gas. So let us understand on which part the speed of analysis is really dependent, and this is the linear velocity. The speed of analysis depends on optimum range of linear velocity or the optimum speed of the carrier gas. Now, these three different carrier gases, they have different optimum linear velocities, and let me show you with the help of Van Dimter curves, and here they are. So if you look at this particular three different curves, nitrogen, helium and hydrogen, now there is a average linear velocity plotted across x-axis and the height equivalent to theoretical plate or height of theoretical plate is plotted across y-axis. So linear velocity is going to influence the height of the plate. Now in this case, if the height is more, the height of the plate is more, you will end up getting the lower plate count. So what is called as the high efficiency method? The analytical method for which the height of the plate is minimum. So you have to look at the region of the or the range of the linear velocity in which the plate height is minimum. So if you look at the nitrogen, now what is the point where the height of the plate is minimum? And you can say that at around 10 centimeter per second linear velocity. But the problem with nitrogen is the height of the plate drastically increases upon increase into the further linear velocity, and hence the nitrogen has very narrow optimum range for the linear velocity. The second one is the helium, the green colored line, right? The helium, if you look at the what is the lowest what is the velocity or the linear velocity at which the helium gives the lowest possible plate height, and it is around, let us say, 15 centimeter per second. And then if you look at the helium curve, it is not as like nitrogen. So this curve has a little slope, and because of that, the optimum range for the linear velocity of helium is quite good. So it can start from, let us say, uh, uh, what is given over here, it is around, let us say, 22 centimeter per second to around 35 centimeter per second. Now, when you look at the hydrogen, if you look at the hydrogen part, then the hydrogen has a much flat curve, right? It starts with the least plate height at the 30 centimeter per second linear velocity, but it can further be used even up to 60 centimeter per second. So, what is Van Dimter, the curves explains to you? Nitrogen has the least range of linear velocity. Then comes the helium, and hydrogen has the most wide range for the linear velocity. And these are the linear velocity ranges. There can be slight change here and there, but this is just the figures to make you understand which one is having the least linear velocity range and which carrier gas is having the highest linear velocity range. So in this case, hydrogen is having the highest range for velocity, then comes the helium, and then comes the nitrogen. So what is the impact of this? The impact is what the analysis will be much faster with hydrogen as compared to helium and nitrogen. Let me show you with the help of an example over here how this impacts onto the speed. Now look at the three different chromatogram. The first chromatogram is with nitrogen as a carrier gas, where 11.7 centimeter per second is the velocity of the gas. The second chromatogram belongs to helium as a carrier gas with the linear velocity of 23.2 centimeter per second. And the third chromatogram belongs to a hydrogen as a carrier gas with the linear velocity of 48 centimeter per second. Now, what this chromatogram is made with different speed? Why this chromatogram is made with a different speed? One is nitrogen with around 11.7 centimeter per second, then helium is around 23.2, and hydrogen is with 48 centimeter per second. Now, if you look at the resolution, so all these chromatograms result into almost similar kind of resolution. Nitrogen with 11.7 centimeter per second gives 1.76 resolution. Helium with 23.2 centimeter second gives 1.67 resolution. And finally, the hydrogen with 48 centimeter per second gives 1.65 resolutions. Though these speeds are different, the resolution is almost one and the same. Nitrogen requires the lowest speed to achieve the similar kind of resolution, whereas hydrogen can meet the same kind of resolution with much higher speed. Now, if the speed of hydrogen is much higher, you must think that then the retention time will be much lesser in case of hydrogen. And you are absolutely right. Now look at the retention time of the peak number 2. It is 6.2 minutes in case of hydrogen. It is 13 minutes in case of helium and 24.5 minutes in case of nitrogen. So which chromatographic or which carrier gas result into the fast chromatography? Is it nitrogen? Is it helium? Or is it hydrogen? Answer to this question is the hydrogen. In spite of the higher speed, lower retention time, it's end up getting the similar kind of retention resolution which is possible by nitrogen and helium, but for these two carrier gases, you are going to compromise onto the runtime. For nitrogen, you need to have the retention of 24.5 minutes. So just understand the speed of analysis. So which carrier gas gives the highest speed? And it is the hydrogen. And hence the hydrogen wins over again helium and nitrogen. Let us talk about the last point, and that is the viscosity of carrier gas. So if you look at the viscosity of these three carrier gases at 50 degrees Celsius, you will find that the viscosity of hydrogen is 9.4. Then comes the helium, which is much higher. That is the yeah, I think the sign over here is mistakenly wrong. So let me correct the sign over here, and it must be greater, right? So helium is hydrogen is having the smaller viscosity, which is 9.4 as compared to helium and as compared to nitrogen. So the viscosity of helium and nitrogen is almost similar. 20.8 is for helium and 18.8 for nitrogen. But if you look at the viscosity of hydrogen, it is much lower, 9.4. So what is going to happen, in case if the viscosity of the carrier gas is higher or lower, and the viscosity of the carrier gas again gets changed, varied with the change in temperature. So if you look at the viscosity of hydrogen, you will find that there is a not much change in the viscosity of hydrogen found with the change in temperature. But if you look at the viscosity change in nitrogen and helium, you will find they are much higher by increase in the temperature. So the viscosity of the carrier gas increases with the temperature. Now, why this change is important and how this change can influence chromatography? Because in case of gas chromatography, we are actually going to play with the column temperature from low to high. And this low to high change in the column temperature is also going to change the viscosity of the carrier gas flowing through the column. So how this viscosity or how this change in the viscosity of the carrier gas is going to impact the performance? Let us discuss this point. So viscosity determines the column inlet pressure. Higher is the viscosity, higher will be the column inlet pressure, or we call it as the back pressure in case of HPLC system. It is called as the inlet pressure in case of gas chromatography. Higher is the viscosity, higher is the inlet pressure. This is the statement, and this statement is going to help us understanding the next point. Now, due to low viscosity, the inlet pressure with hydrogen will be much lower with the same linear velocity as compared to helium and nitrogen. What this indicates? Helium and helium and nitrogen being a more highly viscous carrier gases, they will yield the higher inlet pressure. And if the higher inlet pressure is there, you cannot flow the more carrier gas through the column. You will have the limitations. But in case of hydrogen, being a low viscous carrier gas, it actually yields a very low amount of back pressure. And that makes possible of having the higher linear velocity for the hydrogen. Now this difference in viscosity makes possible to have the higher linear velocity for the hydrogen, but which is not in the case of helium and the nitrogen. Now understand the statement. The high inlet pressure due to helium and nitrogen will further force to keep low linear velocity to have low plate height as case of in case of Van Dimter equation. Because if you increase the velocity of the helium and nitrogen, you will fail miserably in achieving the plate counts. And for that reason, you need to keep the low linear velocity in case of nitrogen, and it is also true for the helium also. And because of this difference, in the linear velocity, hydrogen being least viscous can be operated with high linear velocity and yield short runtime till achieve same performance as that of helium and nitrogen. And I'm sure that you still remember these three different chromatograms. Hydrogen can be operated with the higher linear velocity, which is not possible in case of helium and the nitrogen. And as hydrogen can operated with the higher linear velocity, which increases the speed and hence increases the speed of separation, right? And hence the hydrogen wins again over helium and the nitrogen. So what is the overall conclusion? And let me show you on the screen. So if you look at the speed, the nitrogen is the going to give the slow speed. Helium is going to give the fast speed, but the hydrogen result into the ultra fast chromatography. Resolution is poor with nitrogen, good with helium, and excellent with the hydrogen. In case of efficiency, it's poor with the nitrogen, it's good with helium, but excellent with the hydrogen. What about the runtime? Runtime is long with nitrogen, short with helium, and very short with hydrogen. The cost of gas, nitrogen is much economic, helium is costly, but hydrogen is not costly, and hydrogen is economic. And even in case if you think of using the gas generator, it will be much cheaper. Analyte response. In that case, nitrogen is having the excellent response, and helium and hydrogen gives the average peak response. Now, what is the overall conclusion? The overall conclusion is the hydrogen is better than helium and nitrogen. I hope you must have now got the new perspective how hydrogen is better or the best than helium and nitrogen. So in case if you want to get this kind of very informative videos and content, don't forget to join the Pharma Growth Hub. So there is a link given in the description. You can click onto the link and join Pharma Growth Hub. Thank you so much.